Hello, everyone. It's me, Mr. Younger. I'm teaching conceptual physics, and we're using the 13th edition of Hewitt's conceptual physics textbook. So my lectures more or less stick to the theme in that book, and I'm going off right now with the chapter one, which is called About Science. If you have any questions or concerns, or if you're not following exactly what's going on with the course, make sure you contact me via my email, or, as I said in my syllabus, text messages is probably the most reliable way to get a hold of me. But always, when you do that, make sure you let me know your first and last name and what class you're in. If you have specific questions on practice tests or homework problems, I suggest you take photographs of them and email them to me, and then including the multiple choice answers in the event that it is a multiple choice question that you have a question about. So let's go ahead and get started. I'm going to share my screen with my iPad just to get us started. And like I said, this is chapter one from 13th edition of Paul Hewitt's Conceptual Physics. Let me share. Okay. Any minute now, you should be able to see my iPad screen and a page I have in my GoodNotes. This is a picture of William Thompson, who's also called Lord Kelvin. He's actually a distant relative, if you will, of Paul Hewitt. But anyways, he's been quoted in your textbook, and I'd like to read that quote because this is chapter one about science, and specifically section 1.1, which is scientific measurements. I often say, again, this is Lord Kelvin's words. I often say that when you can measure something and express it in numbers, you know something about it. When you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science, whatever it may be. So, whatever subject we're talking about, until you can make a measurement and it be a relevant measurement, it's not really approaching science yet. And of course, measurements require numbers, and therefore, numbers require math, and therefore, science requires math, which we'll get to a little bit later. I did mention here at the bottom another statement I'll put on there. Of course, measurements made for scientific purposes must be relevant to the science and readily reproducible. As we'll learn throughout the semester, as well as this beginning chapter, we'll learn various scientific methods, and what you learn from that teaches us that not only are measurements relevant, but specifically the measurement you take for it to be relevant has to be a relevant measurement. Meaning, if you're wanting to know, why cars get a certain fuel economy, probably their color. If you were to get an RGB code for the color of the car, that's going to have no relevance whatsoever on whether the car gets good gas mileage or not. So that would be an irrelevant measurement. Whereas the horsepower of the engine might be a good relevant measurement to make, or the torque that the engine can produce, or the wheel ratio, all sorts of stuff like that can be relevant. The mass or the weight of the car, the aerodynamics of it, those are all things that could, in some sense, be measured. Of course, when you go talking about things as broad as horsepower and aerodynamics, there's a whole branch of science associated with even figuring out what it means to say something is aerodynamic versus not aerodynamic. So not only can you just not make a measurement, but you don't even know what measurements to make right now because you're not, and I'm not in the field of automotive engineering, so I don't really know exactly what measurements they make to test the uh, uh, air resistance of a particular vehicle. So that's just a common point. Now, in addition to all that, even if you make a measurement, if you've got a measurement based on numbers and systems of units that you use here in your particular state or in your particular country, there's no guarantee that anybody else in another state or another country is going to use those same system of units. And in fact, they might not even know what they are. Luckily, we've progressed quite a bit beyond that. Around the time of Napoleon, for instance, we switched to a system international, metric system, if you will, that was based on a logical system of units. And it also recognized the reality that if we're actually going to do science, we have to all agree on what measurements we're making and what units those are so that we can all reproduce those experiments. Reproduction is how you can verify someone else's claim, and if you can't reproduce it, that's how you can discard the finding. So let's go ahead and move on with the rest of the chapter. I think between this opening statement by Lord Kelvin and this paragraph I gave you under it, you probably can figure out a lot. One thing we will be using is the SI system, which a lot of people just call the metric system. It's also called the MKS system because it uses meters, kilograms, and seconds. And those are sort of the base units, even though the kilogram technically has a prefix on it, it's still considered the base unit. Normally, the base unit would be the unit without the prefix, but the gram is such a small unit of measurement, it's not that useful in everyday life, so we switched to the kilogram. That being said, you have a system of prefixes that go before it. Mega, for instance, represents a million of whatever you have. So if you have, for instance, megagrams, that would be a million grams, which would be 1,000 kilograms. Kilo is 1,000, and then hecto and centi are basically tens and hundreds, and so on and so forth. You can see those prefixes in the covers of your book as well as in appendices or on the web, and we'll get to that as time goes on, because right now we're just trying to introduce you to science in general and specifically the measurements we make. So let's move on. One of the important measurements that was made, and your author chooses to follow the ancient Greeks in this case, was it was a measurement made by Eratosthenes. So Eratosthenes was a librarian at the Library of Alexandria, a whole museum set up there now. In fact, it's my understanding that the latest Library of Alexandria has been built somewhat close to, if not exactly in the spot of what they think the original Library of Alexandria was built. The main thing being that they recognize that was a great loss due to war, a fire, and we're not really sure what else motivated it, but it may have been uh, a reluctance to look at the perspective of things outside of their personal religions and dogmas and stuff of that sort, but we're not completely sure. So it's very interesting to bring up Eratosthenes. I did begin a timeline for you guys, so you ought to have some idea where Eratosthenes was in the history of mankind and history in general. I didn't finish it, but I'm going to turn to that real quick just to give you an idea of the orders of the various people that come along. So let me roll across to that. You can see one of the three groups of names or four groups of names us teachers often use is Socrates, Plato, Aristotle, and Alexander the Great. The reason being, in many cases, is that Socrates was the teacher of Plato. And Plato, by the way, is sort of not unlike the character of Eratosthenes, as your book mentions. Eratosthenes was labeled beta because he seemed to be at least the second best at everything. Plato was sort of a similar case. In fact, his name Plato means something like stone or broad or something like that, if I remember correctly. And that was because he was a big, burly, strong man that was actually a master in wrestling and things like that. So he was really not just the quote unquote nerds like you see me and people on Big Bang Theory, but he was actually quite prolific and aggressive, not just in science, but in other realms of competition as well. So, anyways, Socrates was a teacher of Plato. Plato was a teacher of Aristotle, and Aristotle was a teacher of Alexander the Great. Alexander the Great also happened to be the son of the King Philip II. Uh, so that gives you a little bit of idea, but we're talking now about Eratosthenes, who you can see comes along and was born roughly in 276 BCE, BCE meaning before the Common Era. We no longer use the BC, and AD. We use before the Common Era and CE, the Common Era, and partly because the before Christ didn't really jive with all of the religions because he's not considered uh, anointed in all places. And in addition to that, he probably wasn't born on that zeroth year either. So it's just a good overall reason to do it was to switch to before the Common Era and after the Common Era, which just becomes Common Era now. So before the Common Era uh, is listed BCE as BCE, and after that period is listed as CE Common Era. So you can see that after Aristotle came Euclid. Euclid would have been born in 325 roughly and died in 270 BCE. Aristarchus, who we're going to talk about in this chapter as well, he was born around 310 BCE and died around 230 BCE. Eratosthenes, who we're talking about now, was born roughly in 276 BCE and died in 194 BCE. And Archimedes, who you had the chance to talk about, whether it be in lab or later on in other chapters, will remain to be seen. But the main thing is Archimedes is another scientist you've heard of, and he was born circa 287 BCE and died around 212 BCE. So we're nowhere near even the Enlightenment period or the Renaissance or any of that stuff. This was all at least 1,000, if not, depending on who you're talking about specifically, to 1,600 years before all the major scientists that you're probably most familiar with, the Newtons and the Galileos and Copernicus and so on and so forth. So hopefully this helps you a little bit. I am in the process of sort of updating this and trying to put leaders down in their time frame, and specifically the three major cultures that we study in Western civilization, which would be Egypt, Greece, and Rome. Of course, I'm just not formally educated in world history, so I can't bring in the other embassy, or excuse me, other empires than those without a lot of work, anyways. So let's get back started on where we were, which was how did Eratosthenes measure the Earth? So how Eratosthenes measured the Earth was a quite ingenious idea. He understood about geometry, and you'd be surprised how much stuff people knew at this time period, because you're probably thinking along the same lines as I did, as when they were using quote unquote Roman numerals. I've never seen any advanced mathematics done with Roman numerals, but clearly they had the ability to do some mathematics. And in fact, we use Arabic numbers nowadays because that number system was much more convenient. That being said, still people like Eratosthenes, Archimedes, and these people living in hundreds of years before the Common Era, those people were able to make really grandiose conclusions about things like the volume or the area of a parabola or the area of a circle and stuff like that without, quote unquote, the calculus, obviously, which was invented by most likely Isaac Newton. To some extent, Leibniz might have, but I think the most recent scholarship suggests that Leibniz did not uh, really invent the calculus as much as he borrowed it from Newton. So, anyways, let's go on. How did Eratosthenes actually measure the Earth? Well, he had read that there was a place south of Alexandria called Syene, in modern day Aswan, and he had learned that they actually had a well in town, and that on the summer solstice, which is roughly June 21st, the sunlight from the sun at noon would actually shine all the way down to the bottom of that well, so that you could literally see your own reflection in the water in the bottom of the well all the way back up and the light around it. Now, if you dig a well and it's, of course, vertically downward, then it automatically points to the center of a spherical Earth. So we know for a fact that any sunlight that runs into a well in Syene and actually hits the bottom of the well must be from beams of sunlight that are coming straight on perpendicular to the ground and therefore headed right to the center of the Earth. With that, he was able to use some simple geometry to make sense of exactly how big the Earth was. So just to give you some perspective on that, I thought I'd pull up Google Earth and show you roughly where we're talking about. So let me stop sharing for this a second and let me share my a different screen. So I'm going to actually share a screen now, and this is Google Earth. And you can see there's America and South America listed down there. But first thing we're going to look for is Aswan. Actually, let's do Alexandria first. Alexandria, Egypt. We'll do a search, and you're going to see where that is, and you'll see it's actually at the near the mouth of the Nile. Excuse me, I don't know where I said Isle. It's roughly in this area, and if you zoom in a little closer, you can see the modern day uh, Library of Alexandria, which is right here. Alexandria Bibliotheca. So that is roughly where we think the original one was, but it's definitely where the new one is, and that this would be roughly the area of Egypt where Aristarchus worked and lived. And what he read about was a place south of them called Syene, that's modern day Aswan. So I can do a search for Syene, and it actually knows enough about history that it corrects for me. So now I'm going to do a search and show you where Syene is. I'm probably horribly mispronouncing these things. Now, ideally, this measurement, if it were to be made to determine the radius of the Earth, you'd really need it to be on a specific great circle, because great circles are the paths of minimal distance for starters. But not only that, they're centered on the Earth, and we're basing all the geometric arguments in this as if we were looking at this from the center of the earth and trying to measure the radius there. So we really have to have that. But this is the town that they would call Aswan. If you go a little further down, you'll see there is a dam, and your textbook author mentions this dam as being roughly where it is. So somewhere in this area would have been where that well was that light could shine down on. So this gives you some idea. Let's back up and just see roughly what the area looks like. Now, in order for him to do this, for Aristarchus to do this, he needed, or excuse me, Eratosthenes to do this, he needed a town due south of them, or at least on a great circle of the planet. He needed another object on that great circle, and he needed to know something about exactly what happened with a shadow cast at Syene versus Alexandria. And that might make no sense to you yet if you haven't read the book. It certainly doesn't. If you haven't ever studied it in the past, it certainly doesn't either. But the main thing is you can, in principle, figure that out. But you have to know roughly how far away Aswan is from Alexandria. And you can use like this little tool in Google Earth. And from that, you could see, for instance, if I measured roughly from here, excuse me, roughly from here up, you start to get around 800 kilometers in this area, and that's roughly what your author was talking about. If you go over to here to where this is, it's a little bit bigger. So I'm not exactly sure how much researches went into exactly where in Syene this experiment was done, that sort of thing, but I can just tell you it's roughly 800 kilometers here, and that should do us. So now that you've seen this part of the Earth, let me scroll back. I'm going to get rid of this measurement device. I'm going to scroll back so we can just have a big picture of the Earth again. And you can see, of course, there's Italy right here, Sicily. There's Greece in this area, and Asia Minor. This is, of course, Saudi Arabia and India over here, so on and so forth, and African continent. But now we'll stop sharing and go back to my iPad so I can explain exactly what was done. So as this comes back up, I'm going to draw a picture. I'm going to try to use the features that my GoodNotes program has as much as possible. So first off, I'm going to try to draw a circle. And that circle was really obviously corrected by my program, which is a good thing. Now, what we're imagining in this scenario is the rays of light coming from the sun are all perfectly horizontal in this drawing. And that just is because we know for a fact, for instance, that the rays are that the rays of sunlight coming from the sun actually emanate as if they're coming right from the center of the sun in every possible direction. But once you get far enough away, the possible directions of the ones that are hitting us, since the sun is so much bigger than the earth, all of them are basically parallel by the time they get to the surface of the earth. So that's what we're looking at here. I can go ahead and make sure you understand that this is the direction the light rays are going just by putting little arrowheads on it. But the main thing that happened is if you draw a line from the center of the planet, or yeah, from the center of the earth, if you will, to a point on its edge, that line, since it's from the center, would actually be a radius. So this distance of this, or the length of this blue line, would in fact be the radius of the Earth. However, this distance would also be, so would this distance, so would this distance. All these distances are radiuses, if you will. None of them were actually drawn that well because I didn't use my nice little feature, but I'm going to try to use it now. And it looks like right about here should be a perfectly radial line. Now, what I want to do is imagine this ray of light extending into the earth to some extent, so I can actually make sense a little bit of the geometry that's being used. So I'm going to take another ray of light and just draw it straight across here like this and let the computer correct it. Now what I'm going to do is draw a line from the center of the earth out of the ground and up to creating basically a pole. So this pole could be a pillar that was built in Alexandria. It could be a tree. It could be a sign, whatever. The main thing is what what Aristarchus was doing was he recognized that there would be some kind of well, if you will, in Syene, and maybe we can draw that a little better. I think this will work. I'll do it this way. Now, this is obviously way deeper and way wider than the actual well is, but the point is that that would be a well, and this was in the place called Syene. Oh, yeah, I forgot. When I've got it on this program that actually draws neater, it can't deal with things like nice little arrows. So this would be Syene right here, and then up here, this location, that would be Alexandria. Oops. Okay. And what he found was specifically that this pole right here casts a very specific shadow. The shadow would be like this. And there's a couple ways you can look at it. One thing he noticed was that the distance from the ground to the top of the pole was 8 times larger than the length of the actual shadow. So if the shadow had a length x, the pole had a height 8x. That's one way we could actually use this, but it's a little more complicated to see that. However, there is another way, and that is making use of a geometric fact. And a geometric fact that I want to make use of here is that when you have two parallel rays like this, okay, if they are parallel, then a lot of stuff happens that can make life kind of neat. And when we draw two lines side by side and we put an arrow on them that points the same way, that means those two lines are parallel. If the lines look like this, obviously they would not be parallel and we wouldn't put those rows on it. Now, the other thing we can do is we can cross those parallel lines, which you can sort of think of like railroad tracks. We can cross them with a bisector. So this is my bisector. Oh, there we are doing the automatic neatness again. That's ruining my ability to write. There's your bisector. And these are your parallel rays or parallel lines. And there's a theorem that we learn in geometry that basically says when you have two parallel rays cut by a bisector, then angles that correspond are equal. And what do I mean by correspond? Well, if you imagine this angle right here, notice that has one side that's green because it's on the bisector, and it's got the other side, the bottom, that's blue because it's on the parallel ray. Well, if you realize right here that's the same scenario, then these two angles are in fact corresponding angles. This angle is corresponding with this angle. This angle corresponds with this angle. This angle corresponds with this angle. So those are all corresponding angles. And when the rays are parallel, then corresponding angles are equal. Now you can go a little further as well. You could say, for instance, this angle right here and this angle right here. Notice they are both between the parallels, so we call them interior angles. So this area is the interior. So all these angles, this one, oops, all these angles, this one, this one, this one, and this one are all interior angles. We've already learned that corresponding angles are equal, but what we're now going to point out is that alternate interior angles are equal as well. So this angle right here is interior and it's on the right side of the bisector. This angle right here is interior and it's on the left-hand side of the bisector. So it's on alternate sides of the bisector and they're both interior, so they're alternate interior angles. So what I'm going to do is call this A I1, alternate interior angle 1, and this is AI2. Those two angles are equal. That's because there's a fundamental idea in geometry that when you have two parallel rays cut by a bisector, alternate interior angles are equal. Here's another alternate interior angle. I'll call that AI3. And here's another one. I'll call that AI3. So those two are equal as well. So now we've learned not only that corresponding angles are equal, but also that alternate interior angles are equal, provided the rays are parallel. So if I were, for instance, to cut a bisector across here, you'd see that this angle, well, let me do it with my laser pointer, this angle and this angle are alternate at interior, but they're clearly not the same angle. You can see this one's very close to 90 and this one's nowhere near 90. So you can see that when the bisector runs across non-parallel rays, none of this is really true. But now we can go back to our drawing. Oh, I should also mention, if you just take two lines and draw them like this, let's see. Well, this right here is called a vertex. And angles across a vertex are called vertical angles. So this would be vertical angle 1, and this would be vertical angle 2, and VA1 is equal to VA2. Because they're vertical angles, all vertical angles are equal. Now, I would also could point out that this angle right here, which I'll call vertical angle 3, is equal to this angle right here, which I'll call vertical angle 4, because those two are vertical angles. So that's just some of the geometry that we're making use of. If you'll notice, this line that I have drawn from the center of the earth through the bottom of the well at Syene, that is exactly parallel to the rays of sunlight. And the red line up here is one of the rays of sunlight. So this line and this line are parallel. So you can clearly see that this angle right here and this angle right here are alternate interior angles. So from that, he was able to measure specifically that this angle right here was 7.2 degrees. So let me do this in black right here. This angle is 7.2 degrees. And because alternate interior angles are equal when the bisector crosses parallel rays, then that means this angle right here is 7.2 degrees as well. Now, a proportionality exists when you're comparing parts of a sphere or parts of a circle and stuff like that. Specifically, if you take the angle, the small part over the large, let's say small over large, you could say, well, the angle is the small part, and the large part is the other angle, 360 degrees, because you know a circle is made up of 360 degrees. But then you could also say, well, the small part of the arc length is the distance between Syene and Alexandria. So I'll say Syene to Alexandria. That's a small distance. And that should be in equal proportion to 7.2 over 360 with the circumference of the Earth. So sorry about that not fitting, but the distance to Syene being the small part and the large part being the full arc length around the globe, that would be obviously circumference. And we know, for instance, circumference is given by c equals 2 pi times r. What we found was Aristarchus, excuse me, Eratosthenes, looked it up and asked some people, and come to find out it had actually been surveyed, and the distance between Syene and Alexandria was approximately 800 kilometers. So, whenever you have a proportion like this is two ratios set equal to each other, is called a proportion. And now it's technically a rate if the units of the top and bottom are different, and it's called a ratio if the units of the top and bottom are the same. You can see the ratio 7.2 degrees to 360 degrees. That is truly a ratio because it's not a rate. Those have the same units. And similarly, 800 kilometers to the circumference of the Earth is also a rate is also a ratio as well. So what we got is 7.2 over 360 is equal to 800 kilometers over the circumference of the Earth. And the way we do such a mathematical operation is we take the diagonals and we cross multiply them. So when I multiply 7.2 times c, I get 7.2 times c. And now I take the other diagonals, which is 360 times 800. Now that's a big number. I'm going to write it down, but we're going to find out it's a lot simpler than it needs. Uh, there's a simpler way to deal with it, but either way, I'm going to take 360 and I'm going to multiply it by 800, and that gives me 288,000. So what we got, 7.2c is equal to 288,000 kilometers times degrees. So this is a degree, this is times the circumference, degrees times circumference, which should come out in kilometers, equals 288,000 kilometers. Now all we have to do is divide both sides of the equation by the coefficient of the variable. So I'm going to divide both sides by 7.2 degrees, and that's going to give me, in fact, C is equal to 40,000 kilometers. So you can just verify that for yourself. Say 288,000 divided by 7.2 gives me 40,000 kilometers, and that was what he argued the circumference of the Earth was, which is actually really, really close. In fact, you can now say circumference is equal to 2 pi r, and that's equal to 40,000 kilometers. Therefore, R would be equal to, all I got to do is take the 40,000, I'm going to divide it by 2 times 3.14159, and I get 6,366 kilometers. The actual answer, by the way, is 6,378. So the true modern result, which is made by much better technology and measuring devices, was 6,378 kilometers is the radius of the Earth. So you can see that's not very big. If I did 6,378 and subtracted from it 6,366, that is a difference of 12. Now I divide it by the accepted value, 6,378, and then I move the decimal two places to the right to make it a percent. I get 0.18% error, which is really, really way better than Eratosthenes was able to get. He didn't quite get that good, but the main thing is with these rough numbers, that's the numbers we got, and it's pretty good. Okay, so 6,378 kilometers is really the measurement of the radius of the Earth, and he was able to get that quite well. In fact, later on in history, Aristotle will come back and make a measurement like this himself. As you saw in the timeline, Aristotle Yeah, Aristotle was quite a bit after Eratosthenes, and he makes the measurement, but he doesn't use as good of results, evidently, and ends up getting a much, much smaller value. It's on the order of like 50% smaller than what the Earth really was. And some historians have argued that Christopher Columbus might not have even attempted to make the passage around to look for India, if he'd known how large the Earth was, because it's some question as to whether technologically they could have sailed that far around the world. Not really sure. But if Christopher Columbus did actually have Eratosthenes' value, he would have immediately known when he hit land or when he saw land that he was not where he thought he was. He would not have called it India. He would have clearly known that he hadn't gone anywhere near far enough. So. Anyways, that's how Eratosthenes was able to measure the distance, or excuse me, the circumference of the Earth and therefore the radius of the Earth, because by then we also knew enough about geometry to know how the radius or diameter of the Earth was related to the circumference. So he did get a figure, and it was really good. In fact, I think your book says he was within 5%. I got 0.18% with this one, but again, I'm using a lot more digits than I'm justified in using and all that sort of stuff. So that was a really big deal, and I want you to think about that when think about some of the dumb ideas that you'll learn about in chapters 2 and 3 about the crazy thoughts of Aristotle and how he thought about science. You'd be surprised how much they really did know. The ancient Greeks had come before them, and they knew quite a bit, and then they built on that and knew quite a bit, and then what your author calls the Dark Ages, which a lot of people are trying to lobby for that not to be called the Dark Ages anymore, was a very important time in history, but because of everybody being locked into Aristotle's thoughts, it might have held science back a little bit. But the main thing is that Dark Age period. Had it not been for people picking up the knowledge that both the Greeks, or even the Egyptians before them, the Egyptians, the Greeks, and the Romans had created groups of now what would be called Arab leaders, they went sort of through their Enlightenment period and built quite a bit of knowledge in addition to that, and that's why we have so many stars, for instance, named with Arabic names. How we got words like sine and cosine, as well as words like algebra and algorithm. All of those are from basically the part of the role that the Arabic cultures made during quote unquote the Dark Ages. So. Anyways, my history friends will get on me for referring to that as the Dark Ages. We prefer the Middle Ages or something along those lines. But anyways, now we've talked to you about how Eratosthenes actually measured the Earth, and you see the actual calculation. And you might wonder to yourself, what is science? Because that, in fact, is the next subsection of the textbook. And I will tell you, in addition to this method that we just used, that idea of using 8-to-1 ratio for the pillar height to the shadow height at the same time, that is another way you could use it. And more specifically, your author makes a point about this. As long as you find two particular spots on Earth that simultaneously have their shadows either pointing towards each other or away from each other, if those 2 points are on a great circle of planet Earth, and that's any circle that runs on the surface of the Earth whose center is the center of the Earth, as long as it's on that, you can use it as well. And your book is jockeying for you and me and anybody I might know a good distance away on Earth. We would just locate a great circle on the surface of the Earth that goes through both my point and some point where I know someone, and then simultaneously we can use cell phones and see exactly what the shadow heights are, compare those two. In some cases you want to add them, in other cases you want to subtract them, but ultimately that could be used to determine the radius of the Earth right now. There's in fact another way as well. One of the other textbooks we use in physics uses this, but if you go to a really, really large lake like the Great Lakes, not like a small pond or anything like that, I'm talking thing that's on the order of uh, tens of miles across at least, but preferably even farther, you can in principle stand on one side of that body of water and then put up a ladder and climb up that ladder as high as you need to until you can just see where the water's crashing on the shore on the other side. That crashing on the shore on the other side is actually the height at which you're at on this side of the water. So you can use that and a little bit of trigonometry and knowing the distance between you and the location that you're looking at across the lake, you can use that distance to determine the radius of the Earth as well. So I don't know why recently we had a plethora of people that still started believing the Earth is flat. I don't know where that came from, but we readily have tools that we can do even in our conceptual physics that would answer the question and not only tell us that the surface of the Earth is a spherical surface, but that we could also measure that radius to be sure. So, anyways, we'll go on now to what is science. And your book actually points out something. I want you to think of science as a thing because it is a body of knowledge. And using quote unquote these scientific methods, we have accumulated a lot of information. And I'm trying to avoid the saying the word facts because I want you to understand the theme of your book about facts not necessarily being unchangeable. But the main thing is one of the major aspects of what science is it's a collection of things that our most brilliant people in the history of mankind have taught us. So over time, we've had these really brilliant people or lucky people or something like that, and they've made certain discoveries, and we've stockpiled those. That body of knowledge is called science. However, the science is also a verb. It's a thing that you do, and in fact, uh, when we use a scientific method, we are practicing science. So, and again, I want to refrain from using the phrase the scientific method like I just used, because it turns out there's not really one scientific method that everybody uses. And in fact, they don't even jump into the cycle of observation versus prediction versus confirmation. They don't even jump into that from the same spot each time. For instance, if you think about Enrico Fermi, he was one of the first people to start doing a lot of the science that was required to make nuclear weapons and nuclear energy and stuff like that. And he basically had the power to see nuclear reactions and was able to map out everything from sort of a blank slate. Whereas Einstein comes along and just looking at Maxwell's equations, he found a bunch of paradoxes that he couldn't make sense of until he had to come up with the special theory of relativity. So in the case of Enrico Fermi, he knew things that we wanted to know and he went out and set out to discover them. In the case of Einstein, Einstein saw stuff that no one else had even seen, much less had tried to solve. And because of that, he was able to postulate an idea purely from thought experiments, what he called Gedanken. And that was how science was done in terms of special relativity and then later general relativity. So science is a body of knowledge, but it's also a way or a verb used to look at the world, and it's sort of a self-checking mechanism. And as time goes on, what we will learn is that by necessity, science will always be right. It's obviously going to quote unquote make some mistakes, but in the long run, it's always got to be right because we have a method by which we make a educated guess, what your book is calling a hypothesis, and then from that educated guess, you can make predictions. You can follow the ideas of that hypothesis, make predictions, and then measure or observe to see if those predictions are true. After those predictions go through hundreds and hundreds and thousands and hundreds of thousands, and in some cases even millions and tens of millions of observations. And once they've never been found uh, to be an error, then that hypothesis might include or might be now called a law or a principle. And in fact, if it's big enough, and it encompasses enough areas of expertise, we might even call that hypothesis a theory, both of which, the principle, the law, or I should say all three of which, a principle, a law, and a theory are all things that we have verified experimentally numerous times and never once been found to be an error. Whereas a hypothesis is sort of a scientific, educated guess that we make, but it's assumed sort of to be factual, but we don't really trust it until after we verify it. Once we verify it, then we feel a little bit more confident, and once more people verify it many other ways, we get more and more confident. But at any point, We can completely find one experiment that completely makes the whole thing fall down. And that's what Einstein was trying to say when, let me paraphrase here, when he said, no number of experiments will prove me right, and it only takes one experiment to prove me wrong. That's a very difficult thing to achieve, but it's also the reason that science is so strong because it doesn't matter who's doing the testing, how they're doing the testing. If they come up and find something that refutes something we believed in the past, then we have to throw it away as long as we can reproduce it, no matter who made it or whatnot. So that's some definitions of science. Science we see is not only a body of knowledge, it's a way of thinking. There's even an attitude behind it. Your book talks about the scientific attitude, and the scientific attitude has a lot of different aspects, one of which is infinite curiosity. It's not okay for us to go out and just play with a frisbee, say, and not think about why does the frisbee always turn left when I throw it with my right arm, and when I throw it with my left arm, why does it turn right? Uh, I can't just play that now as a educated scientist without thinking about why exactly is that happening. That's the curiosity that scientists need to be. Another aspect of the scientific attitude is that not only are we infinitely curious and we're want to know why things do what they do or how they do what they do, in addition to that, we also have zero tolerance for liars. It's not that we're necessarily more moral in everyday life, but in the scientific realm, when we make a publication, if someone ever discovers that we falsified data or did something wrong and didn't admit it or lied about a result or any of that, our careers will be over. Maybe we might get a job as teaching science or something like that, but that's about the best we could do. We're not going to be taken seriously within the scientific community if we blatantly lie. That's also sort of, what we have to keep in mind when we think of experimental results. If someone ever claims something is falsified or claims something is one way and you later find out that they have falsified data, then that's a problem. Andrew Wakefield's a case in my mind right now. We've since learned from his publication that was eventually thrown away. Uh, basically was distanced by all the scientists that were part of it. But basically, Andrew Wakefield, we learned, had a competitor. He had invested in a competitor company in making vaccines, and with that competitor company, he had introduced a vehicle of vaccines that didn't have thimerosal in it, and then somehow all of a sudden he started to notice a correlation between kids having autism and kids taking their thimerosal slash mercury based vaccines. Well, we've since discovered that all that data that he said was pretty much made up, and that he also had a conflict of interest that he didn't tell us about, specifically that he was invested in a company that was making a competitor's brand. He was eventually ran out. I think the last I heard, he's practicing in Texas now, but he was from Great Britain. But that's the case in point, and in fact, that's led to what we call the fake sciences, which is pseudoscience. So that's another thing about science is you got to have an attitude of no mistakes are allowed if the mistakes were dishonest. If the mistakes were just mistakes, you might get ridiculed and picked on. For instance, Pons and Fleischmann, I think, were the two chemists that made a mistake thinking they found cold fusion. And they're still, very good scientists, but they just made a mistake. They didn't understand the nuclear physics behind it enough to understand what was going on, so they thought they had found nuclear fusion. That was just a mistake, a lack of knowledge, and they still got ridiculed and they lost a lot of credibility. But at the same time, they're not completely ruled out of science from that. So hopefully this explains science a little bit. Uh, your book does go on and talk about these great circles and shadows pointing to and away from each other at the same time and using the internet and phones to be able to do that. So there are definite ways you can now, to this day, still figure out that the Earth is not a flat object and that it is a circle or a sphere. It's actually an oblate spheroid, so it's compressed at the North Pole and South Pole, so that the radius north-south is smaller than the radius east or west. It's sort of bulbous around the midline, around the equator, not unlike myself. So, anyways, uh, let's move on to the next part, which is how did Aristarchus measure the moon? So we have, of course, the measurement of the radius of the Earth, and you might wonder, well, how do we actually figure out how big the moon was, and how do we figure out how far away the moon is, and how do we figure out how big the sun is, and how do we figure out how far away the sun is? So all of these are things that were done in ancient Greek, so they actually knew all this. So I wanted to talk to you about how he measured the moon. What Aristarchus had noticed, if you pay attention to life, you know that there's things that happen on Earth, specifically solar eclipses and lunar eclipses. In a solar eclipse, what happens is the moon gets between the Earth and the sun and blocks our vision. But when that happens, it's a very small swath across the planet that gets to experience that solar eclipse, and it's only in that little swath of land where the shadow is big enough to completely block out the image of the sun. So if you know that happens, then you can sort of make an estimate, and this is the estimate that Aristarchus made. Let me start off by drawing a circle to represent Earth, and let me draw a smaller circle to represent the moon. And what we're going to see is light rays that come from the sun. Actually, I'm going to pull it a little bit this way. The light rays that come from the sun fall very close to an infinitely small spot once they hit the Earth. In fact, it's usually on the order of a couple hundred miles across that little swath is, but this is where the shadow would be during an eclipse. This little area right here is the only one experiencing the shadow, and I've actually drawn it quite a bit larger than it is. That's a little too large. But the main thing to understand is whatever this distance is from here to the center of the Earth, or actually in this case we'll just talk from the center of the moon to the edge of the Earth, whatever that distance is, it's approximately the same at all times. It's not exactly the same, we do know that, but what we do know is during a solar eclipse, the shadow of the moon on the Earth is essentially zero in size. So the size is really close to zero. That means that the shadow basically throttles down from the diameter of the moon all the way to diameter of zero. So we know that's the amount of taper. So the amount of taper in shadow from sun and moon is 1 moon diameter. Okay. Now, if you repeat the same process during a lunar eclipse, this one, remember, was a solar eclipse. If you repeat the process with a lunar eclipse, then you'd get something like this. Ooh, that's supposed to be a circle. It did not make it. So, and what we have over here is again the moon. This time it's a lunar eclipse though. And what we can see is that the shadow that the Earth casts on the moon, remember this same angle that we saw here is going to happen again, only this time it's an angle like this. And what Aristarchus had noticed was that when this is the case, this shadow happened to be, according to Aristarchus, 2.5 moon diameters. Now you can do this by just watching, for instance, through a whole lunar eclipse, and you'd see the instant the shadow of the Earth starts to hit the moon on one side, then you'd see that it would completely go over the moon, and then the other end of the shadow would cross across the moon's face. And by doing that, you can see exactly how long it took for that shadow to completely cross. And what you know is going on is that the Earth is moving and the moon's moving, and you can use those relative rates to figure out exactly how fast the moon moves. It turns out the moon moves one diameter roughly every hour, if I remember correctly. But with that knowledge, he was able to put together that the shadow, which was tapered, by the way, by one moon diameter, is 2.5 moon diameters bigger than the moon, or it's 2.5 moon diameters, and therefore bigger than the moon. That means the moon's diameter, so therefore, moon's diameter is about 1 over 3.5 times the Earth's diameter. That was the discovery he made. Now, we had found the Earth's radius was 6,378 kilometers. He found it was 6,366 is roughly the result we got. But we know it's 6,378. So if we take 6,378 and divide it by 3.5, we get 6,378 kilometers divided by 3.5 is equal to 1,822 kilometers. That would mean that's the radius of the moon, and that's actually a fairly good result, a fairly decent result. So we can figure out the actual size of the moon. The moon is almost one quarter the size of the Earth. It's a little bit bigger than a quarter the size of the Earth because 1/4 would be a quarter. This is 1 over 3.5, so it's a little bit bigger than that. And that's a fairly precise figure. So that was how Aristarchus was able to actually determine the size of the moon relative by using relative to the Earth, both using the solar eclipse and the lunar eclipse. You might ask, well, how was the distance to the moon found? Well, this involves something kind of neat. You've probably seen it. I know, for instance, there's a scene on Apollo 13 in which Jim Lovell, the leader of the mission for Apollo 13, is in his backyard in Florida and he's looking up at the moon, and he's actually doing it way wrong, by the way. He's using the thumb to cover the moon. Right. If you really want to cover the moon, you're going to have to put your arm quite a bit further away because that thumb actually, that thumb covers a whole house right across the street from me, so it's a little bit big. But the main thing is that is something you can take, for instance, a button and tape it to a window, and assuming you're looking in a direction that you've seen the moon out that window before, then you can just wait for the moon to come along and look how far back from the button you have to be for you to see the button to be the same size as the moon. When you do that, what you discover is that the distance you are away from the button has to be 110 times the diameter of the button. So that gives us some knowledge. It gives us the knowledge that basically, if I had, let's use a red ray here. So for instance, if I did this and this, well, that wasn't good. Make it a little better here. I went up, what, about 3 from there. So this is up 2.25, and this is down 2.25, so that's about right. So what we found out is that if this is the diameter of the moon, or the button for that matter, then this distance is 110 times larger. So obviously, I didn't draw that to scale. I can't draw it to scale. It's actually quite a big scale, and it wouldn't fit on this paper. But the main thing is that's what we've learned. If you actually put a button on the window and you wait for the sun to get in line with that button, then you can just barely cover up the face of the moon with the button if you find your eye is 110 times the button diameter away from the button. So not only does that tell us about the diameter of the button, it also tells us about the diameter of the moon. So for instance, I can draw again, let's say from here to here. That was not what I meant. It was supposed to be quite a bit smaller than that. And now I can draw another one. And in this case, we see it only went down about a little bit more than one square. So I'm going to say right here. And again, that was supposed to hit right there. It did not, but this is close enough. So this is a lot better example of roughly what the 1 to 110 is. But the main thing is way over here would be the little button, not even visible. And then way over here would be the actual moon. Okay. So once we know that, we know that if we can figure out either the distance to the moon or the moon diameter, then we can automatically get the other because the ratio is obviously 1 to 110. I'm sorry, I've tried to make that circle fit in right, but it didn't work out right. So the ratio of distance, there I go again with my automatic drawing, the ratio of the distance to diameter is equal to 1 over 110, excuse me, I almost wrote 100, 1 over 110, and that happens to equal the diameter of the moon over the distance to the moon. So what that means is, again, we have a ratio, two ratios set equal to each other, so we could, in principle, cross multiply again. And when we multiply that, what we get is 110 times the moon's diameter. And before we used the moon's diameter that I worked out, turned out to be 1,822 meters. I'll use the actual size right here. Actually, let's do moon. Yeah, let's do moon diameter. And the moon's diameter in kilometers is roughly 3,475 kilometers. Now, that's from one cross multiplication. The other cross multiplication just gives me 1 times the distance to the moon. So what we learned there is the distance to the moon is 100 times the diameter of the moon. Therefore, the distance to the moon is equal to 3,775 kilometers times 110, and that gives me 415,000, roughly 415,000 kilometers is how far away the center of the moon is from the center of the Earth. So that's how we were able to figure out the ratio first by just acknowledging the ability to observe it and to block the sunlight. And then that's also how we were able to measure it. Now, how did Aristarchus find the distance to the sun? Well, in this case, he actually got a little wiser still, and he imagined the sun being off a great distance away, like such. And then he realized if we look at the moon during half moon, what we astronomers would call uh, first quarter or third quarter. So when we looked at that, what he knew was the ray between the sun and the moon was making a 90-degree angle with the light from the center of the moon, or the path from the center of the moon to the center of the Earth, which we would have put right here. So it basically made a right triangle. And with a right triangle, as long as you have, for instance, the distance or the length of one side, and then you know one angle's a 90 and you know another angle, then you can automatically find out what the uh, other parts of the triangle are. So using basic trigonometry, he was able to. All he had to do, though, was to measure this angle. Oh, excuse me about that. All he had to do was measure this particular angle. Darn it, why does it keep doing that? Measure this angle. What he found was that angle was like 87.9 degrees, which was not very good. I think it turns out to be like 89.9 degrees or something like that. So his method was good, but his ability to measure that angle, which is really a hard thing to do, was really, really difficult. And because of that, he got a really bad result. He got a result that suggested the moon was about 200, or the sun was about 100 times, 20 times farther away from us than the moon was. And in fact, the actual moon is 400 times, or excuse me, the actual sun is 400 times farther away from the Earth than the sun is, or excuse me, than the moon is. So that means his technology and his ability to measure were leading factors, but that wasn't really the problem. He exactly knew how to do it. It was just a matter of not having the appropriate technology to pull it off. So we can do that now. But once you have the distance to the sun, then you can use the same idea because it turns out that we know eclipses occur, and that's because the sun's diameter in the sky, it measured in degrees, is about the same as the moon's diameter in the sky, namely about half a degree. Because of that, that means that same 1 to 110 ratio exists for the diameter of the sun to the distance of the sun. And in fact, what we ultimately find is the distance to the sun is 150 million kilometers. So, how did Aristarchus find the distance to the sun? Again, that same observation, 1 over 110. Once you figure out, for instance, the diameter of the sun or the distance to the sun, either one of those can give you the other one. So it's just a matter of determining that. But we already found via this part, which was the distance to the sun. I don't know why I repeated that question, but that was it. Once we had the distance of the sun, all we have to do is multiply it by, or excuse me, divide that by 110, and then that'll give us the radius of the sun, and therefore the, or excuse me, the diameter of the sun. So that's actually what we could do. This page wasn't even supposed to be here. I apologize for that. So you might ask yourself, well, what about math? Why is that? Why is that involved, and why are we dealing with that? Well, it turns out that not only is measurement important, but measurement removes all ambiguity. So one of the dangers of science is it's really easy if you're not being very precise. It's really easy to jump to conclusions that aren't accurate. However, if you make a hypothesis and then make a prediction, and that prediction produces something that you can measure, then you can readily take that measurement and examine the formula that you use or formulas that you made up or whatever, and you can see exactly how much error you'd expect to have in that measurement, as well as how much error you'd have in your hypothesis. And if the actual measurement you make doesn't fit within those error bars, then you know the hypothesis was errant or needs correcting in some way. So the actual implementation of mathematics makes that a lot easier because now we have a definitive smallest value and largest value that any particular measurement must be within in order for us to feel confident that our hypothesis led to a correct prediction. And with that, obviously, you have to have math. So that is one of the major reasons why you have to have math. Another major reason is it turns out that the universe evidently behaves like a clockwork of some sort. In other words, it oddly enough, the universe is very explainable if you use the language of mathematics. So We move on now to the scientific methods, and I highly recommend you read all this in your chapter because, Hewitt gives us all these cool things about how you can use pinhole cameras and work out that ratio of 1 to 110, and how you can see little circles under a tree on a normal day. And if you look closely, you'd realize that those little circles are actually images of the sun. And if the image is exactly the right distance away, namely 110 times the diameter of that circle, up to the hole between the leaves that's making that circle, then you would actually see the image of the sun. So I definitely recommend you doing that. And in fact, I've used that with a colander and stuff like that during a solar eclipse. You can actually take a colander and it'll make a bunch of little hole images from all the holes in the colander. And during an eclipse, instead of seeing circles, you see little crescent suns. So that's something that's kind of neat. Regarding the mathematics as the language of science is what we just discussed. Now we want to talk about these quote unquote scientific methods, and I'm going to defer to your author in this case. He does talk about the scientific attitude as having a mode of inquiry. In other words, that's the curiosity I was talking about. Integrity, that's the basically the agreement that we're never, ever, ever going to be any part of science if we ever lie or be dishonest. And then humility is the ability to make sure that if we find our hypothesis makes a prediction that isn't correct, that we have to just throw that away. I don't care if we put, 40 years of work into it or 3 minutes of work into it. That is the humility we have to have. But he talks a little bit further about the scientific methods, and he says science is a way of knowing about the world and making sense of it. And he sees that one common through of all the quote unquote scientific methods are recognize a question or a puzzle, such as an unexplained fact, and then you make an educated guess, what we call a hypothesis, that might resolve the puzzle. Then you use that hypothesis to predict consequences of the hypothesis. Then you perform experiments or you make observations to test the predictions. And of course, you go into that with a knowledge of what the smallest value you could get and what the largest value you could get, and it still be consistent with the hypothesis, so that if there's any ambiguity that specifically you get something outside of that range from smallest to largest, then you have to conclude it was a failure, that your hypothesis was wrong. And then finally, you formulate the simplest general rule that organizes the three main ingredients: the hypothesis, the predicted effects, and the experimental findings. And that is as good a scientific method as anyone I've ever heard. I sort of tend to think of it as a cyclic process where you see something, you make some hypothesis, and you got to remember the hypothesis doesn't have to actually be have any bearing on reality. It can be basically made up stuff for no reason whatsoever. But as long as you make it a hypothesis that can be proved wrong, then it is a scientific hypothesis. It doesn't have to be able to be proved right, but it does have to be able to be proved wrong. If you make a hypothesis that can't be proved wrong, that is not a scientific hypothesis. No ifs, ands, or buts about it. So hopefully that helps you better understand the scientific method a little bit. Now, what we go on into is the discussion of science, art, and religion, which seem to have, at least science and religion in everyday life, seems to have some butting against each other. But I want to point out they're actually in different domains. Science talks about how things behave and maybe what principles we can ascertain regarding the way they behave. Art is our ability to communicate with one another, through songs, through music, through poetry, through literature, uh, the experience of life, and it gives us, different perspectives of looking at life and why life behaves the way it does and stuff of that sort. And then religion gives us some kind of meaning to life. It gives us a meaning possibly, or it gives us the why. Why does mathematics fit the world so well? Well, that could be you're at least knocking on the door of a religious question at that point. And because they handle those innately different domains, understanding exactly how things behave is the domain of science. Explaining those things in terms of what you've observed personally is the realm of art. And trying to make sense of why the world acts that way and why humans act that way and why animals act that way. That's more in the domain of religion. And I want to point out to you, as your book does, there's a very important thing to recognize about misinformation and pseudoscience. And I want you everybody to know that pseudoscience is not science. Pseudo is literally a prefix that says not, basically, but it's a fake science. I shouldn't say, I think fake would be a better word than not. So pseudoscience is a fake science. And that can be a real hallmark of a charlatan. So it's something you want to pay attention to in everyday life just to protect yourself, but also to protect your health. As I said, Andrew Wakefield basically made a whole generation of people, along with people like Jenny McCarthy and other people, reached various conclusions about the unhealthiness of vaccines, and that's just the most absurd thing ever because our vaccines are really very, very, very safe. They're nothing's 100% safe, but they're very safe, and we do a very thorough calculation of risk versus benefit, and we find that the vaccines we give always are more beneficial than they are risky. So that's why we've had these various vaccines. So I'll just mention that to you. I should say that technology is the application of science to affect life. So this is a way to make our life better, a way to make our life worse, all sorts of different things. And the technology is just the application of science. Whether it's a good thing or a bad thing comes down to what ultimately happens with that technology once you make it, and whether or not that technology was used badly or for the betterment of people. So that's a good thing to remember. And finally, I want to talk about physics being the basic science. And in that sense, basically, we can think of, for instance, the sciences of zoology and biology and botany. They all talk about cells and how they behave, the life sciences, if you will. But all of those principles are based on the laws of physics for how cells behave and stuff like that. But that's not the realm that the zoologist, the biologist, or the botanist studies. They get it down to the cellular and seeing stuff that they recognize from everyday life. They make a note about it. If you look at the other sciences like chemistry, that's the behavior of atoms and molecules and stuff of that sort. Again, down to the point where they reduce down to the laws of physics. So in that sense, physics is the basic science underlying all of them. I hope this is a good introduction to chapter one for you guys. I'm going to go ahead and call it a day, and this should be posted on my YouTube channel. You'll see later. So have a good day. Bye bye.